So the focus for today is on the application of Newton's first law of motion. So let's see this situation. It says a 20 kg block resting on a rough horizontal surface is connected to blocks P and Q by a light inextensible string moving over a frictionless pulley. Blocks P and Q are glued together and have a combined mass of m. A force of 35 newtons is now applied to the 20 kg block at an angle of 40 degrees with the horizontal as shown below. Fine stuff. So they said to us the surface is rough. It means there is frictional force there. So since the two blocks are combined, we can actually assume it's just one block. Fine. Now, furthermore, they say the 20 kg block experiences a frictional force of magnitude 5 newtons as it moves to the right at a constant speed. So when they say it's moving at a constant speed, we know that the net force acting on the 20 kg block is going to be 0. We also know that the acceleration of the 20 kg block is 0. But because the two blocks are connected together, the 20 kg block and the combination with a mass m. So it's safe to say the blocks P and Q, the net force acting on them is also 0. And the acceleration of the two blocks is 0 as well, because it's a system. Fine. Now, the first question says, define the term normal force. Well, I trust you can do that. The second one says, draw a labeled free body diagram showing all the forces acting on the 20 kg block. So I want you to draw the free body diagram for the blocks P and Q, but on your rough work section, of course. Fine. So I think we need to go to the whiteboard for this. So the block, the 20 kg block, we know that it's represented as a dot, and the forces are represented as arrows pointing away from the dot. So the first force we can talk about, because it's on a horizontal surface, we have the normal force. And the normal force, we understand that it's perpendicular to the surface and it's exerted by the surface. Then we have an applied force, which is acting at an angle. It's a two-dimensional force, and we understand that we can't work with a two-dimensional force in our calculations. So we have to resolve it into its vertical and horizontal components. Then we know that we have the gravitational force, or the weight if you like, but this one is always directed downwards towards the center of the earth. So you can say uppercase F subscript G, or you can simply say weight for the symbol. It's up to you. So we know that blocks P and Q, they're actually pulling the 20 kg block. So there's a tension force that is going to the right. But because the surface is rough, we have frictional force that is going in the opposite direction, because it always opposes the motion of an object. But we have to specify the type of frictional force which we have here. So it's the kinetic frictional force. So you can say small f subscript k. So this is the free body diagram for the 20 kg block. And the mark allocation never lies for the free body diagram. If you see 5 marks, it means 5 forces have to be represented. Fine stuff. So now I want us to draw the free body diagram for the combination of blocks P and Q. Well, these ones, they are just hanging, so you can't say there's normal force there. There's no surface. But we have tension force, which is directed upwards because the block, the 20 kg block, is pulling this combination according to Newton's third law. Fine stuff. And then they also have the gravitational force. So because it's moving at a constant velocity, they have to be equal in magnitude, the tension and the gravitational force. Are you fine? But for the 20 kg block, the normal force is smaller than the gravitational force. Why? It's because there is a perpendicular component, or rather a vertical component of the applied force that is going upwards. So if we add it to the normal force, it's gonna be equal to the gravitational force. Whew, that's a lot of information, right? I'm sorry about that. Awesome. So now that we have drawn the free body diagrams, what does the next question say? Let's see. Well, it says, calculate the combined mass of the two blocks. So we are looking for the mass M. Do you see that? So if you look at the free body diagram for the combination of these two blocks, well, you understand that in order for us to find the mass M, because it's on the FG part, we need to know the magnitude of the tension force. That's the only thing we need. But we can't use the combination of blocks P and Q to find the tension. Why? Because the mass is already unknown. So if we don't know the mass, we can't calculate the gravitational force. If we can't calculate the gravitational force, we can't calculate, what am I saying? I don't know what I'm saying. But what I'm saying is we can't use blocks P and Q to find the tension force. So we have to use the 20 kg block, so that if we know the tension, then we know the gravitational force. Are you fine? Then we can safely find the combination of the two blocks, the mass of it, that is. Fine. Now let's go to the statement for the last time so that we can have what? I don't know. But one thing we know is that the frictional force acting on the 20 kg block is 5 newtons. That's one thing that we have. And we also know that we have a force of 35 newtons, which is acting at an angle of 40 degrees. But because we are dealing with a horizontal motion, we only need the horizontal component of the applied force. Do you see that? So we have to tell them that we are looking at the 20 kg block. A scientist is very specific. Now, if we look at the 20 kg block, we tell them that the net force acting on the 20 kg block is equal to MA. I know that it's actually equal to 0, right? Because the system is moving at a constant speed. But you have to start by stating the principle. That's how it is. So what is this net force acting on the 20 kg block? It's going to be F in the X, and we have to assign a direction. Sorry about that. So let's say anything that's going to the right is positive. And preferably, always choose the direction of motion as positive. So here we can see that the horizontal component of the applied force is going to the left. So we'll say it's negative F in the X. Then you say plus. The frictional force is also going to the left. So you say negative Fk. And then you say plus. The tension force is going to the right. So it's positive. Then you say everything equals MA. Fine stuff. Then you say minus. What is F in the X? We know that it's F cosine theta. Do you see that? So what is the size of your force? It's 35 newtons. And then you say the angle is 40 degrees, like that. The magnitude of the frictional force is already given to us. It's 5 newtons. And because the acceleration is 0, you can safely say everything equals 0. So let's see how much you get when you say 35 cosine 40 degrees plus 5. Then you get negative 31.81. And then you say plus t, everything equals 0. So this means the tension force will just be 31.81 newtons. Right. So now that we know the tension force, then we can safely go to the combination of blocks P and Q. So let's go. What is happening with P and Q? Well, we tell them the same thing, that the net force acting on this combination is equal to MA. We always start with the principle. Fine. What is this net force? So because we said anything that goes to the right is positive, it means anything that goes down is positive as well, because this combination of blocks is going down. Are you fine? So in this case, tension will be negative, and then you say plus Fg equals Ma, like that. And then you say the tension force will be 31.81 newtons. What about Fg? Well, Fg, we know that it's mg, right? And the mass of these two blocks is actually m. What is the acceleration due to gravity? It's always a constant. It's 9.8. Then you can safely say everything is equal to 0, like that. Then you take your 31.81 to the right. On your left, you have 9.8 m. This is equal to this much. Then from this point, you divide both sides by 9.8. So let's see how much you get. Then you find that the mass m will just be 3.25 kilograms. This will be the combined mass of blocks P and Q. Do you see that? So we had to draw the free body diagram for the combination as well, so that we can see it clearly. Right. Let's move on. So moving on, we go to 2.4. They say at a certain stage of motion, block Q breaks off and falls down. So how will each of the following be affected when the block Q falls down? So how will the tension in the spring be affected? Think of it. So if we remove the block Q, one thing we know is that, where can this thing write? Hey, I don't know. But one thing we know is that the mass is going to decrease, meaning the weight is going to decrease. If the gravitational force decreases, then the tension force is bound to decrease. Awesome. Now, the next question, which is the last one, it says, how will the velocity of the 20 kg block be affected? So because the tension is going to decrease, then it means the velocity will also decrease. Why does the velocity decrease? It's because if the tension force is now lesser, it means the net force acting on the 20 kg block is now acting to the left, resulting in the 20 kg block to accelerate to the left. Think of it. The 20 kg block is moving to the right, but accelerating to the left. So if it's accelerating in the opposite direction, it's actually slowing down in this case. Yes, and there you have it. And guys, this paper is very special to me. It holds a very special place in my heart. It's because of this paper that I was a top 100 achiever during my time. I'll forever love this paper. It's a very nice paper to me. So I hope you enjoyed it as well as I did. And if you did, you can just let me know in the comment section or give this video a thumbs up. And it's actually going to help other people so that they can see it as you keep on liking it. In case you haven't subscribed to my YouTube channel, please don't forget to do so. Otherwise, thank you so much for watching. Stay put. Let's see you in the next video.